My name is David Hart. I'm the director of the Mitchell Center. We're very glad you can join us, especially during these incredibly challenging times. The whole point of our sustainability talks and the whole point of the Mitchell Center is to grow our collective capacity to create a brighter future right here in Maine and well beyond Maine. Regardless of the specific subject that we talk about every week, these talks explore how leaders from government, from business and industry, from non-governmental organizations, and citizens groups can join forces with faculty and students from many different academic fields to address sustainability challenges. And those are challenges that have a lot of moving parts. They require consideration of many complex and connected issues, as you'll hear, issues related to the environment and the economy, to communities and to cultures, and to our past, present, and definitely to our future. If you were joined a little bit earlier, you will have seen some great talks coming up. I hope you can be here and join us again on other Mondays to learn how we can all work together to make a difference. So I'd now like to introduce today's speakers, Jean MacRae and Cynthia Isenhour. Jean is an associate professor in environmental engineering, an expert in environmental microbiology and many other things, as you'll find out. Cindy is an associate professor in anthropology in the Climate Change Institute, and she has a wide range of expertise that includes ecological and economic anthropology. And Jean and Cindy have been helping to lead a diverse interdisciplinary team focused on materials management that includes a strong focus on solid waste. This team got started in the Mitchell Center more than 6 years ago, and they've been going strong for some time. As you'll see, the work their team has been doing is a great example of UMaine's deep commitment to help solve real-world problems in collaboration with diverse stakeholders from government, from the private sector, from non-governmental organizations, and households and citizens. Perhaps the most important story, part of their story that I think is worth listening to carefully is that sometimes efforts to solve one kind of problem in a complex system can cause different problems to pop up in another part of the system. So how do we avoid these, what some people call unintended consequences? That's the focus of their talk today, making our food system more circular, less waste, but is it safe? And welcome to Jean and Cindy.
Thanks, David. Okay, so thanks everybody for coming. My name is Jean MacRae. I'm the Department of Civil and Environmental Engineering here at UMaine, and I'm happy to be presenting with you to you today with my friend and colleague Cynthia Isenhour, who is in the Department of Anthropology and Climate Change. And I would say she has been sort of the leader booting us in the butt to get us to work really hard on the systems in Maine, how to make our systems more circular, but do it in a really thoughtful way so that we make sure that our food system stays safe. The work that we're going to be talking about today was funded by the Environmental Research and Education Foundation, and we had basically startup funding and opportunities to get together through the Mitchell Center at UMaine. So I first wanted to introduce you to the Materials Management Research Group. We're a multidisciplinary group of researchers at UMaine, including faculty and graduate students, like some incredible graduate students, I would say, who have been working on various aspects of materials management for some time. And by materials management, I mean everything from recycling and reuse and considering ways of maximizing use out of things that we extract from the environment. And the beginning stages of this work started with convening groups of stakeholders who included a variety of processors, haulers, activists, legislators, people who are just interested in, for whatever reason, in materials management. And we discovered through the process of meeting with these people that there was really broad agreement that we need to do a better job managing our materials and to classify less material as waste. So that really put us on a road to looking at ways that we could improve the system, where we could uh, step in to tweak the system in such a way as to produce less waste overall. And that's involved incorporating groups of undergraduate students. So we've had at least 3 cohorts of undergraduate students working with us. And we've been thinking about ways to get together to, find funding to work on these problems that are really serious for the state. And one of the things that everybody agrees on is that we need to do better than we are currently doing. Maine was a leader early on in trying to divert more things away from landfill and incineration. So we had some really progressive laws that helped us reduce the overall amount of waste that was being produced in the state. But for many years now, we've actually been sort of stalled at about 30 to 40% diversion of materials away from landfill. And in the last couple of months, there's been a report out by the DEP that shows that we're actually sliding backwards a little bit. So we're diverting less material away from landfill currently. And the goal, the stated and legislated goal for the state, is to reach more than 50% diversion away from landfill. So this is an important issue. Food waste recycling through composting and anaerobic digestion is a way to take a fairly sizable chunk of that waste material and divert it away from landfill and incineration, where food waste causes a lot of the problems that we see with those systems. So diverting food waste and making it, circularizing the system can really help us meet our statewide goals.
Okay, so I'm sure you all are very familiar that there are some wide-ranging challenges associated with food waste. Globally, about 30% of what we grow is wasted. We don't actually end up eating it. And that comes with a wide range of costs, right? So these are economic costs, they're social, and they're environmental as well. So just to give you a few examples of these, in terms of economic costs, it has been estimated that we waste about $218 billion per year. And that's the money that we spend to plant, to harvest, to dispose of food that we don't ever eat. That, of course, comes with a wide range of social consequences, particularly when you consider that here in the US alone, about 1 in every 6th person is food insecure, and that includes around 7 million children. And there are also other social consequences as well when you consider that a large portion of that waste makes its way past low-income and minority communities on its way to landfills, which are disproportionately sited near their homes. There are also a wide range of environmental impacts. So you can think about those as both direct, the food that ends up in our landfills and creates leachate and creates one of the most powerful greenhouse gases, methane, as it decomposes. But also indirect costs. So that's the fuel that we use to plant and harvest food. That's the water that we use to irrigate. It's also all of the materials, that some of them very carbon intensive, that go into food production, like herbicides and fertilizers. And then we get, of course, all of that indirect pollution as well. So the problems with food waste are wide ranging, necessitating solutions.
Just to look a little bit more at the food system, we have a system currently where there are kind of like silos of the system, where we have agricultural production occurring, then the produce may go to a separate facility for processing and packaging. The materials, once they're ready, will go for distribution and retail. Some of these stages may be skipped, but in general, we've got sort of an orderly and separate set of things that happen before the food actually comes to you as the consumer. And the final consumer may be an individual, or it could be an institution, and things will look different depending on who's actually buying the material. But each one of these individual steps along the way is also a linear system where you've got all these inputs like the ones that Cindy was talking about, fertilizer, fuel, water, people, actually all the labor, packaging, the materials that are added to the food. That stuff all goes in at various levels, and there's output materials, whether it's wasted food, which is kind of primarily what we're talking about here, but also the pollution associated with that. So if you look at the agricultural step by itself, the inputs will be fertilizer, pesticides, water. There will be the fuel that goes into the machines that are moving things around. And the waste materials could be uneaten food, things that are not picked for whatever reason, because it's not economical to do that. Poop, if you're growing livestock, there's going to be a certain amount of fecal material that you need to manage. And a lot of the pollution associated with agricultural production is also going to find its way into nearby water bodies, and where it can run off and then wind up causing problems in coastal areas such as the dead zones. So there's a lot of waste and a lot of pollution being produced. And I could, similarly look through at each step along the way to talk about the inputs and the outputs that have negative environmental effects. So one way to try to deal with that is to try to circularize the system. So that agricultural production that relies on the input materials, in particular, I'll talk about fertilizers. Every time you have an agricultural system where you're taking food off of the farm, that's actually moving plant nutrients away from the place where you're trying to produce the plants. So even if there's an internal cycle where produce that's not used gets applied back into the soil in the agricultural system, all the produce that's leaving the farm results in a sort of a net movement of those nutrients away from the farm. So that's why you have to have inputs of fertilizer into the agricultural system to make sure that we can continue to produce food. If, however, you can capture some of that waste material, the food that gets wasted all through the system, and process it in such a way as to recover the nutrients, you can reapply that back to the agricultural system. That's the circularization of the system. And what that does is it reduces the amount of input fertilizer that's required to grow the food. So you might think like, well, fertilizer is one thing. You can go to the hardware store and buy some fertilizer. It's no big deal. But about 30% of the energy that goes into agriculture is actually to produce and move the fertilizers from where they come from to the farms. So the Haber-Bosch process is super energy intensive, and it requires a lot of energy to produce the nitrogen. And there are relatively few phosphorus sources on the planet, and there's estimates that over the course of this century, the mineable, usable phosphorus sources are going to be gone. And so in order to make sure that we can continue to eat, which means continue to exist, we need a circular system. We have to be able to recover the nutrients. So turn it over to Cindy.
Yeah, thanks. So some good news is that we've seen some fairly rapid policy momentum around circularizing our food systems, particularly here in New England, where we're, I think, for all intents and purposes, really leading the way with several states now trying to operationalize the food recovery hierarchy, where you rank potential solutions from the most preferred, like reducing waste in the first place, feeding people, feeding animals, before doing things like landfilling, which would be the least preferred solutions. So for example, Vermont now has a universal recycling law, which is graduated all the way down to the household, which prevents food waste from being landfilled. Other states in the region, including Massachusetts, have commercial requirements for food waste recycling. So these are all really positive, advancements. But when we were working with our stakeholders here in Maine, where we don't have similar legislation, we learned from our stakeholders that there are a wide array of competing interests, right? Some were very concerned that if we mandated food waste recycling, that it would actually result in more contamination in our systems. We also see that economic drivers are really important. There's some hesitancy to invest in some of these food waste recovery systems and technologies. They are expensive. And then there are, of course, concerns about equity. Could we design a system that would be ensure equity? So we were really wanted to kind of jump into understanding how might policy be designed in a way, and how could public support be raised in a way that would encourage economic, environmental, and socially just solutions. And particularly, one of the reasons that we undertook this project is because we see such strong policy momentum and the rapid expansion of capacity in developing markets in this space, which really raises the question about how we can do it best. Jean, if you could advance the slide. So we wanted to start asking the question, not to forestall any innovation, but to start anticipating what might the risks be in a more circularized food system, so that we could design carefully and thoughtfully. So we asked a couple of questions, some based on what our stakeholders here in Maine were telling us, questions about whether or not regulation or the mandate or requirement to recycle food waste would increase contamination in these systems and potentially introduce contamination into agricultural soils. What are the other risks, social, environmental? So our research design really attempted to pair kind of two strategies. First, we were really interested in working with food waste processors to understand how they understood risk, what types of risks are on their radar, how do they mitigate those risks, and then also to look at the presence of contamination in food waste feedstocks. So that would include physical contaminants like glass, plastic fiber, chemical contaminants, trace contaminants, and biological contaminants like pathogens or antibiotic resistance genes. And our hope is that through this research, which we have recently finalized, we can continue to work with processors to minimize unanticipated risks or under-anticipated risks. So the first part of that process included starting to talk to processors. So we sent out a survey to all the licensed processors in Vermont, Massachusetts, and Maine. So that's approximately 114 facilities. We got a response rate of about 29%, with pretty equal distribution from the 3 states. You can see here, we did have quite a few composters respond, only 4 digesters, although that's somewhat parallel with what the numbers look like. And we had an interesting array of ownership structures. So 21 private facilities responded, 9 public, and 3 public-private partnerships. And this ranged from very large processors to very small processors, with ranges from 40 tons to almost 13,000 tons of capacity per month. So we asked a variety of questions, and in a short presentation like this, I can't go through all of them, but a few things to note. We did ask folks, in your experience, what types of contamination are of concern when accepting food scraps? And this was an open-ended question. And I just thought it was interesting here to show you a word cloud of the mentions that came up. You can see featured prominently glass, plastic, plastics, stickers, with over 20 mentions of these kind of what we would categorize as trash. We also had fewer mentions, but some of trace toxins. So for example, arsenic, pesticides, cleaning chemicals, 5 mentions of sharp objects, and then 4 mentions of process inhibitors. So for example, things like sodium that could really upset the balance of a digestion process. We then asked them of the things that they had listed, which were the most significant risks. And it's worth, I think, noting here that trash, again, features prominently. These are oftentimes visible contaminants that if they make it into the final product, can really damage the brand, can damage its residual value and use value going forward. Could I have the next slide, Jean? Thanks. We also asked them to tell us about how they perceived risk by generator, so based on where the food was coming from. And you can see here, if we think about the sources of waste at the bottom of this chart, so institutions like schools, colleges, hospitals, residential customers, restaurants, grocers, food distributors, food processors, and food producers, you can think about that range as integrating complexity as it moves through the system, right? So with food producers, we see fairly low levels of perceived risk, largely because of what they're sending to the facilities is more homogeneous. It tends not to have been mixed with a lot of packaging material. And then as you move to food processors, there's slightly more risk introduced. As you come all the way to residential and institutions, there you might have the potential to get pre and post-consumer waste. There could be cutlery, there could be packaging materials. So that risk increases as the food products move their way through the system. Okay, back to you, Jean.
Okay, so the question then is, where along this circular system can contamination be introduced? And at each stage, there are different things being done, and so different risks tend to be introduced into the system, or different contaminants tend to be introduced. So where agricultural production is happening, fertilizers, pesticides, potentially antibiotics are used quite widely in the production of livestock. Pathogens and trace contaminants can come in. So by trace contaminants, I mean the things like heavy metals and trace organic materials. And quite often, those aren't actually added in on purpose the way that fertilizers and pesticides are, but they may contaminate irrigation water or be air pollutants that are dropped on the soil, and therefore they contaminate the soils. So the location of a particular farm can influence the degree to which there's trace contamination available to cause problems or to accumulate in the agricultural produce. From a processing and packaging standpoint, there are additives added into foods to make them last for longer. Packaging is added to try to reduce the likelihood of spoiling of the food before it actually gets consumed, or at least goes to a consumer. And depending on the way that the materials are stored and managed, there can be an increase in the number of pathogens in the system. So certainly in meat processing, there's always a danger of introduction of pathogens into the system through the process of slaughtering the animals, because there can be fecal material that'll contaminate the meat. In the distribution and retail side of things, there can be additional packaging, so that can happen at the distribution or retail level. Again, the temperatures of storage can amplify the amount of pathogens that are present in the end product. Cleaners may be introduced into the system, and if they're stored for some time, nobody really likes to think about this, but there's always the opportunity for vectors to get in, and vectors are things like insects and mice and rats and stuff that are going to be attracted to the food that may ultimately leave behind contaminants in the food system. Once it gets into the end consumer's sphere, I put down household items here, but it could also be institutional items. Whatever is actually being used in the area where food is being prepared or served or used. There's opportunity for things to be misclassified. So as the consumer is thinking about how to dispose of the waste food scraps or the waste materials that are generated during the processing of the food. So if I'm chopping vegetables, like the middle of the core of my pepper or whatever, so that material will wind up in the compost bin, but it's possible that I can also introduce other wastes into there. Again, temperature control is really important for the control of pathogens and the amplification of those. And, in a home, there could also be pet wastes and other things that are introduced into the compost, and it could be fine depending on what is allowed into the system. what the waste processing end of things, the waste management does is it takes a material that is perishable and therefore can generate odors, and it's kind of unstable. Ultimately, it's really nasty. Food waste is nasty, but the stuff coming out of a waste management, a well-managed composting facility is not nasty at all. It's like really nice soil and it smells good. So what's happening in the process of treating the waste is that it's being stabilized. And by that, I mean that the really easy to degrade material has broken down. It's at a constant temperature. There's really not that much change in the volume of the material. And it's basically now a good amendment to soil. It's got good organic matter, and it's got some residual nitrogen and phosphorus that act as fertilizer for plants. So it's a really good thing to add to agricultural soils to reduce the requirement for input materials. During that process, some of the contaminants that were introduced early on may degrade. So if they're biodegradable organic materials, they can be degraded. The problem is there are lots of things that come into the system that aren't degraded during this process. So you can have a stable material at the end of treatment, but if there are heavy metals in the system, they won't degrade. They're elements and they cannot be destroyed. Similarly, there are organic components, trace organic components that are not biodegradable. That's it's part of what attracts us to various industrial chemicals is they're super stable. So you can store them and they're not going to degrade over time. Those things also don't degrade in waste management. So these are the places where the contamination can be incorporated into the system. And we wanted to measure how much contamination there actually was in our particular system. So we were looking at the two regulatory environments, whether there's mandated diversion of food waste or voluntary diversion. In the case of Maine, all of our contributions to food waste management are voluntary. Whereas in Massachusetts and Vermont, there's sort of a staged rollout of the system. And at the time when we sampled, none of the no residential customers needed to separate their food waste. So all of that was voluntary, but the larger generators all were mandated to separate out food waste. So those were mandated diversion types. And we had 6 different source types from grocery stores, restaurants, hospitals, schools, retirement communities, and residences. First, what we did to the samples was to weigh them, remove all the physical contaminants, weigh those, and catalog what was actually in there. And then we processed all the food waste down to a smooth paste so that we could measure what was inside. So the first things that we measured were the physical contaminants. And so this is mass of physical contaminants divided by the total mass of the sample that came in. And what we found was that regulation did not affect the contamination level. So this was contrary to our original idea that based on what our stakeholders had said was that, you know, if you force people to compost, they're not really going to care about it or be that educated about it, and they're just going to dump whatever they want into the compost bin. And that's not what we saw. So that's good, because it means that it's going to be possible for us to push that lever and encourage people to start separating out their food waste. What we did find was that the source influenced the physical contamination. So if you actually look at the graph that I put here, the non-regulated samples actually looks like it's higher than the regulated samples. And it is significantly higher. But if you take out the grocery samples, because our main grocery samples were all being depackaged after the fact. So we took out all of those samples from our analysis because it wasn't fair, because they knew that they were going to be going to a depackager. So we took out those samples. And then when we took out the grocery sample grocery samples from the states where it was mandated, the difference was gone. So this value moved up, and so the difference between the two was gone. And it was interesting to see actually that the percent of contamination in the grocery samples, which comes before the consumer in our food chain, there's less contamination down there, as you would expect, compared to those end consumers. But we did see a lot of variability in all of our samples. And so just, small number of samples here. So the actual differences between these source types should be taken with a bit of a grain of salt. Heavy metals, we measured in these samples, and we were looking for a suite of toxic heavy metals, as well as a few that were related to electronics. And the toxic heavy metals were absent for the most part. We have zinc and copper can be toxic at high levels, but they're also required nutrients for proper growth and good health. So we found them at concentrations that were well below even the most stringent international regulations for application to land. So we basically found that this source separated food waste was not a significant source of heavy metals to the soils. And so this does not represent any kind of threat to our system. Next, we're looking at halogenated organics. So these are materials that can get into the food system through the use of pesticides and herbicides. They're also present at low concentrations in the atmosphere and in water because they're used as industrial chemicals, and industrial chemicals that are released into the environment, even in really, really low concentrations, can in some cases accumulate to dangerously high levels through the food web. So that's called bioaccumulation. And it's when materials that are in the environment at low concentrations are taken up by an organism, whether it's a plant or an animal, and it partitions into the flesh of the organism, which makes it get up to a higher concentration. And each of us over our lifetime is actually accumulating the stuff that we get, that we're in contact with, if our body doesn't have a mechanism to excrete it and get rid of it. So since most of these halogenated organics are synthetic chemicals, so they're not normally found in nature, there aren't a whole lot of pathways for them to be destroyed. And so that's why they tend to accumulate, and it's why they're of concern in the environment. So in our experimental design, we measured these compounds using what's called EOX, so extractable organohalides. And that's a bulk way of measuring all of the organic halogenated organic materials in a given sample. And what we found were, even though this method has a pretty high detection limit, but it incorporates everything, even though we have this high detection limit, 14% of our samples were positive for EOX. And that gave us some pause, because we don't want these things in our food system at all. However, the concentrations that we found were lower than the only limits that are out there, which are in Europe, for adsorbable organohalides, which is a similar method. So they're not at really alarming levels, but it's definitely cause to keep our eye on that particular ball. Of greater concern to me, at least, was that we took a subsample of our samples and we sent them off for PFAS analysis. So this is for fluorinated organics. So that this is, they're also halogenated organics, but they are harder to measure than the other kinds, the chlorinated and brominated kinds. And more than half of our samples had PFBA, which is a compound that has been used as a substitute for, some of you may have heard of PFOA, which has sort of voluntarily been removed from the market. And the problem with PFBA and all of these PFAS compounds is the fluorine to carbon bond is probably the strongest one that there is. And these are just they're going to stay for a really long time in the environment. So if they start to get into the food system and magnify there, that's a serious concern. So this is an issue that I am worried about. And it's still not 100% clear where that's coming from, because certainly PFBA is not added on purpose into agricultural systems, but it is a component of quite a bit of food packaging and food contact papers to try to, so there's a potential entryway into the food system through that. The last set of contaminants are the biological contaminants. We looked for pathogens that are typically found in food waste. So we looked for 3 of them. Salmonella is is one of the most commonly found foodborne illnesses in the US. It's also the most dangerous in terms of the number of deaths that typically happen each year. Listeria is one that's of interest because it's not red, like as soon as it gets into food, it's going to continue to grow even if you keep the food cold, which is, contrary to what most other foodborne pathogens do. And we did detect those 2 pathogens, but we did not detect E. coli, Shigella toxin producing E. coli. So we didn't find them in very many samples. Listeria it's not good to see it in all those samples, but it was also present at very low levels. And this is waste, not food that's going to be consumed. So we think that this is probably a bigger problem for people who are handling the solid waste than it is going to be in the agricultural system, because chances are these pathogens are going to be killed off during treatment of the wastes. On the right over here, I have a graphic of a subset of samples that we sent for high throughput sequencing. And we looked for genera that have foodborne pathogens in them. Not that every member of a particular genus of bacteria is going to be a foodborne pathogen, but we were just looking for the ones that could potentially be pathogenic. And what was interesting to me was that, at least in one sample, we had a high percentage of Yersinia, and Yersinia enterocolitica causes foodborne disease, but Yersinia pestis is the cause of plague. So anyway, I don't think we have plague out there, but it was interesting to find a fairly high concentration of this particular organism. Turns out that it's Asta, the graduate student who did a lot of work on this, also looked to figure out why the heck we had so much Yersinia, and apparently it's not that uncommon to find it associated with food that doesn't make people sick. So we think that's going to be an issue primarily for people who are handling the food waste, not so much in the food system in general. The antibiotic resistance genes is a different issue. That's where bacteria can acquire genes from the environment that make them resistant to being killed by antibiotics. And we use antibiotics to treat infections. And if the pathogens that cause an infection are not sensitive to an antibiotic, you can have a runaway infection, and you can be killed by something as simple as a cut on your finger. So it's important to maintain the viability of the antibiotics that we have, in particular because there's very little research going on into alternatives at this point. Unfortunately, we've been using some of the older antibiotics like tetracycline and penicillin in the production of meat animals, and and dairy animals. And that has caused an increase over time of resistance genes in the environment. And there is some fear that we're going to, and we've already seen an increase in resistance among pathogens as well. So there's a fear that during treatment, we put organisms in an environment that is conducive to them trading off these genes, because these antibiotic resistance genes are often on mobile genetic elements, which allows them to share them with neighbors. So that's not a good thing. Almost all of our samples had some antibiotic resistance genes in them, and at levels that are a little bit higher than you expect to see in natural soils. The good news, though, was that we didn't see any resistance to colistin, which is the last resort antibiotic that people use in the event that somebody gets an infection that has multiple resistances. So we have not been using in the US colistin as a growth promoting antibiotic, which is good. In Asia, where they have been using it, they discovered this MCR1 gene, and it's been increasing sort of rapidly over time there, which really shows the connection between agricultural use of antibiotics and the presence of antibiotic resistance genes in the environment. So it's a bit worrying that we have these higher levels of antibiotic resistance genes in the food, but super glad to see that we didn't have resistance to colistin.
Thanks, Jean. So as we move toward our conclusions, I want to just point out that when we think about risk in the system, as Jean pointed out, it can be introduced at multiple locations. And our work with facilities, food waste processing facilities, really is only able to take kind of a snapshot of a very distributed system of risk. You know, we were looking at the risk introduced through different food waste generators, risks associated with, are we sorting or are we mixing our waste with other non-food waste? How do we collect it? Is it a mandatory environment or is it a voluntary environment? But of course, we didn't do any post-processing testing, so this is all inputs. And we also have to, give the disclaimer, a lot of the contaminants that we saw that were of most concern are things that are introduced in a much larger system, and that food waste processors have very little ability to detect oftentimes, and significant challenges mitigating those risks. If you would advance my slide, Jean. When we talked with processors about what types of mitigation strategies they do employ, and they've got a wide range, the food waste processors that we work with are all working very hard to ensure that their systems are clean. So they use processes of inspection, making sure that they inspect every load that's coming in to make sure there's not contamination, sorting that out. They also do a considerable amount of education for all their food waste generators, what's acceptable, what's not acceptable, physical separation, right, going through and hand picking contaminants out. They also will practice enforcement and terminate contracts for folks who continuously send loads with high levels of contamination. There is some testing, which we learned throughout the stakeholder engagement process is incredibly expensive and difficult for processors to do comprehensively. And some of them would actually also conduct grow trials where they would grow a flat of beans and in the soil that they're producing to make sure that the growth looked normal. So we'll just point out that these are really important strategies, and then ask the question, these types of mitigation strategies, how do they kind of stack up against things like antibiotic resistance genes and PFAS or other forms of trace contaminants. So we hope that will become part of the process as we move forward, as working with our facilities to think about what strategies can they undertake to think about, plan for, and mitigate some of these unseen contaminants that don't really kind of show up as highly rated in their own perceptions of risk. I think we're ready for the next slide, Jean.
Just to conclude, what we saw in this work is that mandating source separation didn't seem to result in more contamination of the samples. So we never saw a significant difference between mandated and non-mandated, apart from that original physical difference that we thought we were finding. The fact that the physical contamination was in the opposite direction of what we were expecting points to the potential importance of the outreach and education that occurred in the rollout of the legislated required separation of food waste. So in the process of doing that and getting people to comply, they learn and they figure out how to do all this stuff right so that you get a clean input material. The issues that we did find that were of concern were those halogenated organics, especially the PFAS compounds that are very, very difficult to remove from a system once they get in, and they can amplify in the system. And the elevated levels of those antibiotic resistance genes are of sort of broad concern. And what we don't really know yet is how those are affected by the treatment composting and anaerobic digestion. So the jury's still out on that. In the literature, there's some reports of those antibiotic resistant genes going up, and there's other reports of them going down over time during treatment. And so there's more that needs to be learned on that subject.
Another conclusion for me is that, some of these contaminants are outside of the realm of responsibility for the processors. And yet, when there are instances of contamination, they can be held morally, legally, and financially responsible, which, to me suggests the need for a stronger regulation of some of these contaminants, and making sure that they don't end up in our system by removing them earlier in the process. And then I think Jean and I agree that, going back to the original question that we posed, we need to make our food systems more circular. We can all agree on that. And is it safe? We think it can be, and we hope that this research can contribute to thinking about systems that are safe for all of us so that we can have healthier and sustainable circular food systems.
Can we give them a hand, even though they can't hear us, for this just wonderful, wonderful talk? And we have people are writing things into the chat, not just questions, but how great the talk was. So it really, really just raised lots of questions that people have. And I'm just so pleased to have a chance to gather some of those and think about what we can do in terms of all of this. So one of the issues really is, what can we do? So all the people that are listening, are there steps that we could take? Are there things that we should do?
Yes. So first, do compost your food waste. It's you can't have a circular food system if people don't participate in it, and if things go to trash. One thing I didn't really stress too much during the talk was the downsides of adding food waste into landfill. So food waste, I think I saw a question that came up, like how much of landfill is actually
Yes.
food waste, and it really depends on the landfill. But the range of food waste in our total waste that actually goes to landfill or generation is probably in the low 20% range. So in some places it's much higher, the massive food waste compared to total waste. So at least 40% of the mass of waste is organic matter that could be composted. So between food waste and yard waste. So it's a pretty significant portion of the total amount of waste that we produce. And the real issue with landfilling food waste is it's wet, which produces more leachate, and it's active. The degradation of the food waste in landfill releases methane, which is a strong greenhouse gas. It produces these organic acids that solubilize metals that make the leachate worse. It's releasing organic matter into the leachate, which is a headache for the folks at the landfill to deal with. So there's a lot of downsides to having food waste, which should be a valuable resource in the landfills. It's also no good in incineration, just by the way. Too much water.
Oh, thank you. Another question people were interested in, Why do states differ? So what are some of the factors that seem to cause states to differ in their approaches to food waste management? And can we learn anything from that?
Do you want me to take that one, Jean? Yeah, it's a really good question. And I think that the answer is probably really complex. But one of the things that we know about this region is that landfill tipping fees do tend to be higher in New England than they are in other parts of the country, which our colleague Travis Blackmore in economics has pointed out is probably part of the reason that this area has been more inclined to put in some restrictions on landfilling food waste. It's expensive, right? And so we should be able to get some more economically efficient solutions for folks. So I think that's part of the answer is what are the incentives for people to act on this? That being said, I think part of the question was also, do we need a more kind of standardized approach? And I do think there is a potential that that could be coming and on the horizon. We've seen several pieces of legislation proposed that would encourage more widespread access to composting and digestion opportunities. Here in Maine, it's for folks who are really interested, it's tough, right? There are very few programs available for people to participate in either curbside collection. So we're kind of on our own in most markets. We have to do it in our own, on our own in our backyards. But there are a growing number of private groups, particularly in the southern part of the state, that are collecting food waste and composting. So I think it's coming, and hopefully we can do it safely.
In the talk, you mentioned Europe. What can we learn from them, and what can they learn from us in terms of this whole issue?
Yeah, we can learn a lot from each other. It's interesting that there's a clear effect of culture on how we deal with waste, because the Europeans, well, maybe culture and also density of where people live and how close they actually are to their landfill. But Europe has gone much quicker than we have on trying to divert wastes to a greater degree, and on trying to recover more things so that they're not being landfilled and incinerated. So really minimizing the use of landfilling and incineration. So we can learn that we need to do that, and rely less on landfilling and incineration overall. But they've got quite a bit worked out on the incineration front to actually. So there are times when really the only option is to landfill or incinerate, and that's going to be in time where you can't guarantee the safety of the circular system, or when the that there are toxic materials. So they've gone a little bit further down the road also of banning things that they expect to be those kinds of contaminants that can result in really no other alternative but to bury it and entomb it so that it's never going to come in contact with people and animals and plants again, or burn it to destroy it. So the organic contaminants that are potentially toxic or harmful in the environment can be destroyed by really high temperature incineration. So when you do that, you really need to control the process so you're not releasing other contaminants.
Thank you. Our world has changed a lot in the last couple of years. Maybe this is a question that's not possible to answer, but how has COVID potentially affected the waste stream, and what should we be thinking about in that regard?
Cindy, also feel free to jump in, but I'll say that there's definitely a big increase in single usage items. All the PPE that we use, both in hospitals and in our homes, are contributing to an increase in the overall amount of waste. I think sometimes we freak out about the risk of one thing and then we produce a different risk. And normally we're prepared to live with the longer term risk because we may or may not be around to see the outcome. But I do feel like there's you know, there are things that we are prepared to just increase the amount of garbage in order to reduce the risk of transfer of diseases. You certainly see this from the very high waste generation rates in hospitals. Our colleague Debbie Saber has done a lot of work on how much garbage is produced in hospitals. And it's a lot because of the need to protect personnel from infectious disease. So there's that. And then there's, you know, for a time we weren't allowed to take our own shopping bags into the grocery store. And still there's places that continue along that line. I think people are buying more packaged food right now because they're afraid of, you know, picking up something that's been handled, like produce that's been handled by a bunch of people potentially before. So I think it has changed things. How fast it goes back.
I think one of the, you know, as it relates to food waste too, of course, if you look at the food recovery hierarchy, higher on that preferred list of solutions is to feed hungry people. And I do think that there, you know, have always been concerns about donating, you know, still edible, but no longer saleable food. And that's a place where we can make some real advances, I think, you know, COVID or not. Let me just give one really positive example. In Vermont, there was a study about the effects of their universal recycling law. And one really cool figure that they came up with is that by instituting the landfill ban for food waste, it increased donations to food or to hunger relief organizations by 40% in the first year. And so that's really positive. And, you know, I think that there are ways also to do that very safely, to, you know, follow all the guidelines for safety, but also contribute to a movement further up the food waste or food recovery hierarchy.
Very, very helpful, very interesting. If we wanted to learn more, and we all do, from you and what's going on, do you have a website that we could look at? And another question, we'd love to have our children learn from all that you're doing. Are there some books that they could look at, or are there some things for children that would be helpful?
We do have a website that does include all sorts of information about what our team has done in the past, including some of our stakeholder engagement efforts. And we don't have it there yet, Jean, but we could post the final report to ERAF on the website so folks could learn more about the study. Boy, Linda, you know I have 3 boys. I don't have a recommendation, strangely enough, on a good book about some of these solutions, but I can certainly get back to you on that one. Jean, do you?
I don't, and I feel a bit dirty and ashamed that I don't have good kids books, because it's like, it's perfect fodder for what kids would find gross and fun to think about.
Oh, we've run out of time, and there are so many questions in the chat group. Will you be able to see those questions after we end? And if people wanted to follow up with you, how would they do it? And everyone, we should all be thinking about who we want to talk to tonight about this great talk, because there's just so much we can all do and learn.
Sure. I mean, email would work great. Yes, thanks, Ruth. Just put our emails in the chat, so we're good.
Yeah, and sorry we didn't get to, there were a lot of really good questions in the chat, so please do reach out. Yeah, there's some great questions about fiber ride, and please reach out, folks. We're happy to engage.
Yeah.
And I just wanted to say before we go, thanks to, I know we have a few of the processors that worked with us on the call, and I just wanted to say thank you to them as well for your willingness to work with us and share your perceptions and expertise. And we
want to spend our whole evening with you and with all your stakeholders and partners to learn from everything that you're doing. So let's give our great speakers a hand. And David, do you have any final thoughts?
So wonderful talk. I've never seen so many great questions before, which I think tells you how important these issues are and how engaging Cindy, you and Jean are. But some other time, I hope you'll come back and tell us what the secret is to great teamwork, because you're all part of a great team and you've helped steward that process. But all the partners, some of whom you just mentioned, and many others that I've seen you work with over the years, is a key to the success of these efforts. I mean, we're going to face complex challenges for quite a while, I bet, but working together, hopefully we can get better and better at managing all of this. So thank you so much. And thanks to everybody who joined today. I think you guys broke last week's 2 weeks ago record, which isn't easy in terms of participants. Thanks, everybody.
Thank you all
Thanks,
for the
everyone.
invitation.